last session under Unit 6, and in this session we'll be looking at purine and pyrimidine. So at the end of the session, you should be able to draw the structure of pyridine and pyrimidine. You should be able to give examples of similar compounds that form part of the DNA. You should be able to compare the acidity of purines and pyrimidine. And lastly, you should be able to provide equations to support both the electrophilic and nucleophilic substitution reactions of pyridine. Okay, so to look at the composition of purine and pyrimidine, or the structural features of purine and pyrimidine, we realize that purine is made up of imidazole, the imidazole ring here, and the pyrimidine ring. So purine is made up of two different aromatic fused rings, a 5-membered ring and a 6-membered ring, and this is also pyrimidine. Now if you look at our basic building blocks of our DNA and RNA, realize that adenine and guanine are analogs of purine, right, or derivatives of purine, whereas cytosine, uracil, and thiamine are analogs of pyrimidine, right? So let's take note of that. So in our DNA, then also, of course, our RNA are composed of adenine and guanine. So both are the same in our DNA and RNA. However, in our the kind of pyrimidines that are found in our DNAs and our RNAs are the ones that change considerably. So the type of pyrimidines that are found in our DNA are cytosine and thiamine, while the type of pyrimidines that are found in RNAs that make up the RNA are the cytosine and uracil, right? So we'll be looking at all these ones in the subsequent slides. Now, if we want to compare the basicity between the two, right, we can compare the basicity of pyrimidine with the basicity of pyridine. Now, pyridine is a stronger base than pyrimidine due to the fact that there's a second nitrogen, which is a heteroatom in pyrimidine, which is electron withdrawing, right? So the electrons are not easily donated to make them Lewis bases because they are closely held together, making pyrimidine more basic than pyrimidine, and consequently the opposite is true for their conjugate acids. So it means that pyrimidine will be more acidic, that is conjugate acid will be more acidic than pyridine, right? So the protonated form of pyrimidine is a stronger acid, whereas that of pyrimidine is a weaker acid. Okay, so in also looking at the acidity of purines and imidazoles, now we know that Lewis acids are electron pair acceptors, right? So imidazole, due to the presence of this electron withdrawing group that is found in the pyrimidine ring in purines, it makes it more acidic than imidazole, right? So both these two structures have the imidazole moiety present. So this is the imidazole moiety in purine, the imidazole moiety here. However, because of the presence of this extra electron withdrawing group of pyrimidine found in the purine ring, which is electron pair acceptor, it draws more electrons towards itself and increases the acidity of the purine ring compared to that of the imidazole ring. So the opposite is true when you look at the conjugate acid and then the conjugate acid of these two. So it means that the protonated form of purine will be less acidic compared to the protonated form of pyrimidine, right? So if you want to look at the acidity of purine and then pyrimidine, then we can see that pyrimidine is more acidic than purine, which in other words means that purine is more basic than pyrimidine. Okay, so in considering the reactions of pyrimidine as well as pyridine, in comparing the two as you can see here, because of the presence of the second heteroatom present in pyrimidine, it makes it less reactive than pyridine towards an electrophile, right? So in electrophilic substitution reactions, you can see that pyridine is more reactive than pyrimidine. However, towards a nucleophile, the opposite is seen. So towards a nucleophile, pyrimidine is more reactive towards a nucleophile than pyridine. So the opposite is true when we talk about nucleophilic substitution reaction. So we would have to take note of that. That is due to the presence of the second heteroatom that is present in pyrimidine, and I explained this with some of the resonance structures that are obtained. So most of the time it's better to use the resonance structures that are produced. So if nitrogen is highly electric, in any resonance structure that puts a positive charge on the nitrogen makes it less reactive. So if by any chance a resonance structure is produces quite a number of resonance contributors with positive charge on the nitrogen, that means it's making the nitrogen partially positive and making our carbons partially negative. So if the carbon is partially negative, then it will be more reactive towards an electrophile. And then of course, if the opposite happens, then it means it will be more reactive towards a nucleophile. So please, let's take note of how to use the resonance structures to explain the reactivities towards a nucleophile or an electrophile. So due to that, pyrimidine therefore undergoes electrophilic substitution reaction only if there's a strong electron donating substituent on the ring. So the presence, because pyridine is not completely reactive towards electrophile, the best way to activate a site on the ring is to introduce an electron donating substituent on the ring. So the presence of an electron donating substituent, typically in this case, the amine group increases the reactivity of the ring. So it activates the ring towards electrophilic substitution reaction, and the incoming substituent, which is the electrophile, goes to your carbon number 5 position. So if you want to count, you have the heteroatom as number 1, 2, 3, 4, 5. So the 5th carbon position is where the incoming electrophile attaches itself to. So this is a typical reaction equation of electrophilic substitution reaction in pyrimidine. Okay, so this is another example for your Perusa nucleophilic substitution reaction in pyridine.